Welcome to the deep dive. Today we're tackling something pretty fundamental but maybe less intuitive than basic arithmetic. Order theory.
Yeah.
It's essentially the mathematical way of digging into what we mean by order.
Yeah, exactly. We all get, 2 is less than 3, or A comes before B in the dictionary.
Right, the basics.
But order theory takes that core idea, that binary relation of less than or equal to, and makes it abstract. And that's powerful. It lets us talk about order in situations far beyond just lining things up. Think about concepts like, say, containment.
Containment, how so?
Well, like saying circles are special kinds of ellipses. That's an order. It's a form of hierarchy, of specialization. Formalizing this means we can find these really general rules, theorems that apply all over the place.
Okay, that makes sense. So if we're formalizing this, what's the first big fork in the road? What distinguishes different types of order?
The absolute key concept is comparability.
Comparability.
Yeah. Can you actually compare any two elements in your set using the order relation? In familiar cases like numbers, the answer is yes. Pick any two integers. One is always less than or equal to the other. That kind of order, where everything is comparable, we call a total order, sometimes also called a chain, simple linear.
Okay, total order, like a number line. It makes sense.
And this is crucial. Many important mathematical structures involve elements you just can't compare. When you allow for that possibility, that incomparability, you get what's called a partial order. We often shorten that to posit partially ordered set.
Can you give an example of that, where things are incomparable?
Yeah. Think about sets of things. Say, the set of all animals. Is the set birds a subset of dogs? No. Is dogs a subset of birds? Also no.
Right. Neither contains the other.
They're incomparable under the subset relation. That makes the collection of subsets of animals a poset, not a total order.
Yeah.
Or consider divisibility on natural numbers. Does 3 divide 13?
No.
Does 13 divide 3?
No.
So 3 and 13 are incomparable under divisibility. Another posit.
Okay, so that immediately changes the picture from a simple line to something, well, more complex, like a network.
Sort of, yeah.
So if elements can be incomparable, how do we ensure there's still some meaningful structure? What rules define a real order, partial or not?
Right, you need some ground rules. The axioms, there are 3 properties of relation, let's call it needs to have to be a partial order. First is reflexivity. Everything is related to itself. Seems obvious, but necessary.
Yep.
Second, antisymmetry. This one's key. If A, B, and B, A, then A must actually equal B.
So no cycles.
Yes.
You can't have A less than B and B less than A unless they're the same thing.
Exactly. It forces directionality. That's what makes it an order. And third, transitivity. If A, B, and B, A, C, then it must be that A, S, C.
The chain of command, basically. If A reports to B and B reports to C, then A is ultimately under C.
Precisely.
Yeah.
Those 3 rules give us the structure.
And that structure lets us visualize these things, right, with those Hasse diagrams.
Exactly. Hasse diagrams are minimalist drawings. They use position on the page, higher means greater, and only draw lines between immediately related elements. It cuts out the clutter from reflexivity and transitivity and shows the core structure.
Okay, so once we have this structure, this poset, we can talk about special points within it.
Yes, and we need to be careful with terminology here. There's a difference between least and greatest elements and minimal and maximal elements.
What's the difference?
A least element is unique if it exists. It's smaller than every other element in the set. Same for greatest element, it's bigger than everything else.
Okay, like 1 in the positive integers under the usual order, it's the smallest.
Correct. But minimal elements just don't have anything below them. There might be several minimal elements. And similarly for maximal elements, nothing is strictly above them.
Right, so let's use that divisibility example again. You mentioned something surprising there.
Yes. On the natural numbers, 0, 1, 2, 3, with divisibility, the number 1 divides everything else. So 1 is the unique least element.
Makes it?
But what's the greatest element? What number is divided by all other natural numbers?
Well, nothing divides 0 except 0. Wait, every number divides 0.
Exactly. 0 divided by 5 is 0, divided by 100 is 0. So under the divisibility relation, 0 is the unique greatest element. It's kind of non-intuitive, but follows directly from the definition.
That is neat. It really shows the power of abstraction, and I'm noticing a pattern here. Least greatest, minimal maximal, lower bound, upper bound. It seems very symmetrical.
That's a fundamental principle, duality. For every concept in order theory, if you just flip the direction of the order relation, replace the store, you get its dual concept.
So least becomes greatest.
Minimal becomes maximal, lower bound becomes upper bound, infimum becomes supremum, and the beauty is any theorem you prove has a dual theorem that's automatically true. You prove one, you get two.
Very efficient.
Very. And this structure pops up everywhere. In topology, the collection of all open sets in a space forms a special kind of poset called a complete lattice. That structure is deeply tied to how the space fits together.
A lattice, right.
Even in category theory, a very abstract branch of math, the concept of an infimum, the greatest lower bound, in a poset is essentially the same as the concept of a product. It shows how fundamental these order-theoretic ideas really are.
Wow. Okay, so the big takeaway isn't just that math can describe order, but that order itself is a much richer, more complex, and often nonlinear structure than we might think.
Precisely. It's about relationships and structure, not just sequences.
But we talked about infima and suprema, like greatest common divisors and least common multiples in the divisibility example. They're clearly vital parts of these ordered structures, these lattices. It makes you wonder what other comparisons we make every day, maybe classifying species or navigating complex choices, could be better understood if we formalize them as, say, a complete lattice, something for you to chew on until our next deep dive.